All right, welcome to the Explainer. Today, we are diving into a single scientific paper, and its goal is so ambitious it honestly sounds a little bit like science fiction. It's aiming to solve, well, almost everything. This isn't just a small tweak to our understanding of the universe. No, this paper proposes a totally radical new theory of the cosmos that could clear up some of the biggest, deepest mysteries in physics all in one go.
You know, our best theories of the universe, things like the standard model of particle physics and general relativity, they're unbelievably successful. But here's the thing, they're also incomplete. They leave us with these massive, profound puzzles that just scream out that there's some deeper, missing piece to the whole cosmic story. So let's take a look at what those puzzles actually are.
Okay, so to really get why this new theory is such a big deal, we first have to wrap our heads around the enormous problems it's claiming to solve. And these aren't minor issues, right? We're talking about fundamental cracks in the very foundation of modern physics.
All right, first up, dark matter. We see its gravitational pull everywhere. It's like this invisible scaffolding that's holding entire galaxies together, stopping them from just flying apart. And get this, it makes up more than a quarter of the entire universe. And yet, we have absolutely no idea what it actually is.
And then you have its even more mysterious cousin, dark energy. Something out there is causing the expansion of the universe to speed up. It's pushing everything apart faster and faster. We've given it a name, dark energy, but just naming it doesn't mean we get it. Not at all. It's the biggest thing in the universe, and it basically thumbs its nose at our current understanding of gravity.
And finally, there's a problem that comes from deep inside our own theories. It's called the hierarchy problem, and it's basically this. Why is the Higgs boson, the particle that gives mass to everything, why is it so incredibly light? According to our understanding of quantum mechanics, its mass should be gigantic, totally unstable. The fact that it isn't is, well, it's like finding a pencil balanced perfectly on its sharpest point and it just stays there forever. It just shouldn't be possible.
So, this is where the new paper comes in. It suggests that these three huge problems, dark matter, dark energy, the hierarchy problem, what if they aren't separate mysteries at all? It argues they actually share a common origin, and that they can all be solved, along with a few other puzzles by the way, just by adding one single new ingredient to the laws of physics.
And that new ingredient? It's called a dissipative Higgs field. Now the key word you really got to focus on here is dissipative. It's a term from thermodynamics, and it basically just means energy loss, like friction. So the theory is proposing that the Higgs field we all know and love isn't the whole story. It suggests it has a kind of partner field that introduces a fundamental friction into the very fabric of the universe.
Okay, so let's really dive into this. How on earth can one single idea, this cosmic friction, possibly fix so many completely different problems? Well, this is where the theory gets truly elegant.
So let's go back to that pencil balanced on its tip, the hierarchy problem. How in the world do you keep the Higgs boson's mass stable when everything we know about quantum physics says it should be spinning wildly out of control?
So check this out. That red line shooting upwards, that's the problem. Those are the quantum effects that should make the Higgs mass just fly up to infinity. But the blue line, that's the new theory in action. This cosmic friction acts like a stabilizing force, like a dampener, and it just cancels out those runaway effects. And not by a little, by an incredible 32 orders of magnitude. Suddenly, that pencil isn't balancing precariously anymore. It's being held perfectly in place.
Okay, so what about dark matter? We've spent decades searching for some new kind of particle, and we've come up completely empty. This theory says, well, maybe that's because we've been looking for the wrong thing entirely. It suggests dark matter isn't a thing at all. Instead, it's just what we see when this new field loses energy. It's a natural side effect of the cosmic friction itself.
And you know what? The same exact logic applies to dark energy. The theory actually calculates that the baseline energy of this new field, its at-rest state, has the exact anti-gravity properties we need to explain why the universe's expansion is speeding up. And it gets better. It even predicts a super precise value for a key cosmological measurement, a value that perfectly matches what our astronomers have already observed. It's a dead ringer.
But the theory doesn't even stop there. It proposes that gravity itself might not be fundamental, that it actually emerges from fluctuations in the Higgs field. And by doing that, the whole framework just naturally resolves one of the biggest paradoxes in all of physics, the singularity at the center of a black hole. In this model, that cosmic friction just prevents an infinitely dense point from ever forming. It's just not possible.
You know, a good theory doesn't just clean up old mysteries, it has to make new, testable predictions. And this one makes a really big one about the overall shape of the cosmos. Based on its calculations, there's a 98.7% chance that our universe is spatially flat. And that's a key feature that aligns perfectly with our best measurements from our best telescopes.
So, okay, the theory is beautiful, it's elegant, but is there any actual evidence for it? Well, this is where the story takes a really fascinating turn, taking us from this deep, abstract theory to a weird little mystery happening right at the edge of our own solar system.
See, for years now, scientists have been scratching their heads over this tiny, unexplained slowdown that's affecting the Voyager 1 and 2 spacecraft. As these probes fly out into deep interstellar space, they're slowing down just a little bit more than all our laws of physics say they should be. It's a real puzzle.
And this is where the theory's predictive power just shines. The model says that the heliopause, that's the boundary where our sun's influence kind of fizzles out, acts like a sort of thermodynamic wall. So, as the Voyager probes cross that line, they start to feel this cosmic friction for the first time, creating a tiny drag force. And what's incredible is that the slowdown predicted by the theory perfectly matches the mysterious deceleration that we've been observing for years. It's an exact match. Okay, so a single, unified explanation for some of the biggest mysteries in the cosmos, and it's backed up by this strange anomaly from our most distant explorers. So what's next? How do we figure out if this is a genuine breakthrough, a real step toward a new theory of everything?
Well, statistically speaking, the idea is already on some seriously firm ground. There's a tool called a Bayes factor, which is basically a way for scientists to measure how strongly the evidence supports one idea over another. And when you run the numbers, the analysis shows that this new theory fits all of our data incredibly well. A score of 13.5 doesn't just mean it's pretty good. It means there is strong evidence that this new dissipated model is a better explanation for our universe than the standard model we're using right now.
And this is absolutely crucial. This isn't just some elegant idea that we can admire from a distance. The theory makes a whole list of specific, concrete, testable predictions. It's saying we should see tiny little deviations in how the Higgs boson behaves at the Large Hadron Collider. It says galaxies should grow in a slightly different way than we thought. It even predicts we could measure tiny time delays in our communications with deep space probes. This is what makes it real science. It gives us an actual roadmap to go out and either prove it right or prove it wrong.
So we're left with this incredibly powerful and tantalizing question. Is it possible that by adding a simple concept from 19th century thermodynamics, just a little bit of friction, to our cutting-edge 21st century particle physics, have we stumbled upon the key that unlocks dark matter, dark energy, and maybe even the true nature of gravity itself? The answer? Well, it's out there, waiting for our next generation of experiments to go and find it.